Hi, welcome to Sunil Maths tutorial, Functional Analysis, class number 6. In this video, we learn a theorem. Let us see the statement of the theorem. Capital N be a non-zero normed linear space. Then, capital N is a Banach space, implies and implied by set of all elements x such that norm x is equals to 1 is complete. So, we prove this theorem. Let us see the introduction part. N not equals to pi, n is non-zero, n is not equals to pi, be a normed linear space. We notate the set as capital S. So S is equals to x such that norm x is equals to 1. You have to understand this set capital S. This set means suppose any element alpha belongs to S means norm alpha is equals to 1. It means capital S is the set of all elements whose norm is equivalent to 1. Whose norm is equivalent to 1. And clearly it is subset to capital N. By the definition of S, it is a subset of N. Now our aim is to show that capital N is a Banach space implies and implied by capital N is a Banach space implies and implied by capital S is complete. So we take N is a Banach space, we prove that S is complete. In the converse part, we assume that S is complete and we prove that N is a Banach space. So right, let us see. Suppose that capital N is a Banach space. We have to show that S is complete. What is mean by Banach space? So Banach space is a complete normed linear space. Banach space is a complete normed linear space. Our aim is to show that S is complete. What is mean by complete? Every Cauchy sequence in the set is convergent, then we say that it is complete. So we have to prove that S is complete now. To prove this, let us take a sequence. Let Xn be a Cauchy sequence. Let Xn be a Cauchy sequence in capital S. It is observable that since S is subset to N, implies as Xn is a Cauchy sequence. Xn is a Cauchy sequence in capital N, because Xn is Cauchy sequence in S and S is subset to N. So obviously this sequence Xn is a Cauchy sequence in capital N. And we know that this capital N is Banach space. And every Banach space is complete. Implies N is complete. What is the definition of complete? N is complete means every Cauchy sequence in capital N is convergent. Implies the sequence Xn is convergent. To a point X in capital N. Now we have to prove that X belongs to capital S. We know the fundamental fact. Norm is always continuous function. We know that norm is continuous. Norm is a continuous function. By applying this condition, Xn converges to X implies as norm Xn converges to norm X. It means limit n tends to infinity, norm Xn tends to norm X. Limit n tends to infinity 1, because of, you observe that we get 1 means Xn is a Cauchy sequence in capital N. We define that this Xn is a Cauchy sequence. This Xn is a Cauchy sequence in capital S. Here we define that Xn is a Cauchy sequence in S. And by the definition of S consists those elements whose norm is equals to 1. Therefore, we conclude that norm Xn is equals to 1. So limit n tends to infinity 1 tends to norm X. This condition implies as norm x is equals to 1. If norm x is equals to 1, obviously x belongs to capital S. Our aim is also same. We have to prove that x belongs to capital S. Already we show that xn is a converges to x in capital N. Therefore, from this we conclude that the Cauchy sequence xn in capital S is convergent to x in capital S. It means every Cauchy sequence in capital S is convergent to a element or is convergent to a limit. It means capital S is complete. Therefore, we conclude that capital S is complete. So we assume that n is a Banach space. We assume that n is a Banach space here. We assume that n is a Banach space, and we prove that S is complete. Now let us go for converse. In this converse part, we assume that S is complete. Suppose capital S is complete. We have to prove that, or we prove that from this we prove that capital N is a Banach space. Already by given data, this N is a normed linear space. Capital N is normed linear space. So N is already a normed linear space. Our aim is to show that it is a Banach space. So it is equivalent to prove that. It means we have to prove that Banach space. It is equivalent to prove that capital N is complete. To prove we prove this N is complete in two cases. The first one, case 1. We prove that N is complete in two cases. Case 1. Let us take xn be a Cauchy sequence. In capital N such that norm xn is equals to 1. Remember this point. We define a Cauchy sequence. In capital N. Satisfying the condition norm xn is equals to 1. By this definition, norm xn is equals to 1. We conclude that the set or the sequence xn belongs to S. The sequence xn belongs to capital S. If the sequence xn belongs to capital S and we have this S is complete. By the definition of complete, every Cauchy sequence in it is convergent. Therefore, the sequence xn is convergent in capital S. And we take the one more element is convergent to x in capital S. It means limit n tends to infinity, xn is equals to x in capital S, and S is subset to capital N. It means the same thing holds in N also. The sequence xn is convergent in capital N. Hence N is complete. In this case. Our aim is also same. You have to show that N is complete. I repeat this part. Observe that. We assume that S is complete. We have to prove that N is a Banach space. Our aim is to show that N is a Banach space. By already given data, capital N is a normed linear space. So it is equivalent to prove that N is complete. To prove N is complete, we use two different cases. One is norm xn is equals to 1, and in the second case, norm xn not equals to 1. So case 1, let us take xn be a Cauchy sequence in capital N such that norm xn is equals to 1. By the definition of capital S, this sequence xn belongs to capital S because of norm xn is equals to 1 means the element xn belongs to capital S. So right, and S is complete. Complete means every Cauchy sequence in it is convergent. So xn converges to x in capital S. So that is limit n tends to infinity xn is equals to x in capital S. And we know that S is subset to capital N. Therefore xn is convergent in, this is not S, xn is convergent in capital N. Therefore n is complete. Therefore n is complete. Now we go for case 2. Case 2. We define the same. Let xn be a Cauchy sequence in capital N. Let xn be a Cauchy sequence. Xn be a Cauchy sequence in capital N such that norm xn not equals to 1. In the previous case we define norm xn is equals to 1. Here in this case we define norm xn not equals to 1. That is the difference between case 1 and case 2. Right. Now define one more sequence. Now define yn is equals to xn by norm xn implies as norm yn is equals to norm of xn by norm xn. This is nothing but norm xn by norm xn. Again the numerator and denominator are same. You get 1. What it means? Norm yn is equals to 1. If norm yn is equals to 1, by the definition of S, S is the set of all elements x such that norm x is equals to 1. So this shows us that yn belongs to S. It means the sequence yn is clearly defined over S. Clearly defined over S. First we show that this yn is a Cauchy sequence. First we show that this sequence yn is a Cauchy sequence. This sequence yn is a Cauchy sequence in capital S. To prove this, consider one norm ym minus yn is equals to, by definition of ym, xm divided by norm xm minus xn divided by norm xn. Right? We calculate norm xm divided by norm xm minus I'm adding one term minus xn by norm xm plus same term I write plus xn by norm xm minus the last term xn by norm xn. So which is equals to, or which is less than or equals to, by splitting the norm xm minus xn divided by norm xm, because here the denominator is same. For these two terms the denominator is same, plus norm xn minus norm xm minus xn by norm xn. So let us simplify this. Norm xm minus xn divided by norm xm plus, here you observe that here is a xn, here is also xn. So by making norm xn common, and by taking LCM, norm xm into, you can write in the numerator as norm xn minus norm xm. That's it. And again you can write like this, norm xm minus xn divided by norm xm plus norm xn into norm. The norm is non-negative function, so you can write norm of xm minus xn, because it is a non-negative function, divided by norm xm into norm xm. Here observe that we remove this norm, that's why we get less than or equals to. Here also again you get this norm xn, the norm xn get cancelled, norm xn and norm xn get cancelled, and we have simply less than or equals to norm xm minus xn divided by norm xm plus norm xm minus xn divided by norm xm. Both are same terms, so you can write like this, which is less than or equals to 2 into norm xm minus xn divided by norm xm. Therefore, final conclusion, norm ym minus yn is less than or equals to 2 into norm xm minus xn divided by norm xm. Let it be equation number 1. So right, now already we have, since this xn is a Cauchy sequence, this xn is a Cauchy sequence. By the definition of Cauchy sequence implies as, for each epsilon greater than 0, there exists a positive integer. By the definition of Cauchy sequence, there exists a positive integer n naught such that norm xm minus xn is less than epsilon by 2. Actually, this is the definition of Cauchy sequence. We can write additionally one more term, norm xm. There is nothing wrong in that one. You can define this RHS as your wish. So right, let it be equation number 2. Now using equation 2 in equation 1. Using equation 2 in equation 1, we get norm ym minus yn is less than or equals to 2 into epsilon by 2 norm xm divided by norm xm. So you observe that here 2 get cancelled, norm x get cancelled. This is less than or equals to epsilon only. Therefore, you simply write less than, not less than or equals to less than. Therefore, we conclude that norm ym minus yn is less than epsilon. Therefore, we write like this: for given epsilon greater than 0, there exists a positive integer, small n naught, such that norm ym minus yn is less than epsilon for all n comma m greater than or equals to n naught. This shows us, this condition or this definition shows us the sequence yn is a Cauchy sequence. In capital S. The sequence yn is a Cauchy sequence in capital S. Our aim is also same. You observe that. First we show that yn is a Cauchy sequence in capital S. So by following this derivation part, we show that yn is a Cauchy sequence in capital S. And what is the nature of capital S? Since capital S is complete. What it means? Every Cauchy sequence in it is convergent. Therefore, the sequence yn is convergent to y in capital S. Remember this point. Now we go for one more. What is the definition of yn? Since yn is equals to xn by norm xn. From this calculation, you observe that xn is equals to yn into norm xn. Hence, here the sequence xn, the sequence norm xn is a Cauchy sequence, because norm is equal to 1. Is a Cauchy sequence in the set of real numbers, and capital R is complete. If capital R is complete, this norm xn or this sequence norm xn converges to a number alpha say. This is just our assumption, because every Cauchy sequence in capital R is convergent. So converges to alpha in capital R, converges to alpha in capital R in the set of real numbers. So it means that norm xn converges to alpha means norm xn into yn converges to alpha into y, because yn converges to y, because yn converges to y. This condition shows us y xn, the sequence xn converges to alpha y, the sequence xn converges to alpha y, the sequence xn converges to alpha y, where that alpha belongs to capital R and that y belongs to capital S. So right, again this S is subspace of capital N. This S is subspace of capital N. This shows us the sequence xn is convergent in capital S. Sorry, in capital N. This sequence is convergent in capital N. So this shows us every Cauchy sequence in capital N, every Cauchy sequence in capital N is convergent. Therefore, capital N is complete. Therefore, capital N is complete. Therefore, capital N is a Banach space. Capital N is a Banach space. This completes the proof of our theorem. Hence, we conclude that capital N is a Banach space. Capital N is a Banach space implies and implied by the set S is equals to the set of all elements X such that norm X is equals to 1 is complete. Hence proved. This completes the proof of our theorem. Right, in the next video we'll learn some additional one more theorem. So I think you understand this theorem. Keep learning. Wish you all the best.